Good morning students. Welcome to the class on real analysis. Today I am going to deliver the lecture on an introduction to real analysis. So real analysis is the study of the concept of calculus. Calculus is undoubtedly one of the greatest creation of the human mind. Calculus is used everywhere in science, engineering and even in humanities. From astronomy, in anthropology, all the way of zoology, calculus is used extensively. Modern physics simply being impossible without a calculus. Since the tools of calculus are used so extensively, it is vital that is, tools are rigorously verified. So, real analysis is the theoretical justification for calculus. Real analysis and the integral part of mathematical analysis are in whole mathematics, which gives us the platform to understand all the developments or advanced branches of mathematics. So, first of all, we need to know what is real analysis. Real analysis is a discipline of mathematics that was developed to define the study of numbers and functions as well as to investigate essential concepts such as limits and continuity. These concepts are in calculus and its applications. Real analysis has become an incredible resource in a wide range of applications. If you write the definitions, there are 2 points are focused, that is real number and real valued functions. So, the definition of real analysis is the branch of mathematics that deals with the study of real numbers and their functions. We need to understand what is real number. So, real number system in which we deals with the study of real is called real number system. The real number consists of all the rational numbers and all the irrational numbers. The rational number consists of terminating and repeating or recurring ones. Irrational number consists of non-terminating and non-recurring ones. So, we further try to understand what is rational number. Rational number is a number which can be expressed by the ratio P by Q, where P and Q are integers provided P is not equal to 0. The examples are, the first one is 5 by 2, the second one is 1 by 2 and the third is 7 by 8. It is in the form of P by Q. Sometimes it can be expressed as the decimal numbers. Suppose 1 by 2 can be written as 0.5. The second one is 1 by 4, which can be written as 0.25. And it is looked at closely, this is terminating one. So, terminating is the one nature of the rational number. Next example is 1 by 3. So, another nature of the identification of rational number is repeating. Consider one example 1 by 3, which can be written as 0.333 etc. This is repeating. So, what I would like to summarize that rational numbers can be identified by the nature of repeating and terminating. Now, we next come to the irrational number. That is the another important aspect of real numbers. Irrational number is what? It is the just contrary to the rational numbers. So, you can easily define the irrational numbers. A number cannot be expressed in the P by Q form is known as irrational number. The examples are pi, which is equal to 22 by 7, which is equal to 3.14285714285. The next example is root 2, which is equal to 1.4141213562. The third one is the exponential. E equal to 2.718281928. These numbers are non-terminating and non-repeating. So, another way of identifying the irrational number through non-terminating and non-repeating. Next, I am going to discuss about field axiom. A field is a set with two operations called addition and multiplications, which satisfy all the familiar algebraic properties. The first property is commutativity. In this property, for all a comma b be the numbers which is in f. In addition, a plus b equal to b plus a. For multiplication, a into b equal to b into a. The second property is associativity. In this property, for addition, for all a comma b and c in f, a plus b plus c equal to a plus b plus c. For multiplication, a into b into c equal to a into b into c for all a comma b and c in f. The third property is distributivity. For all a comma b and c in f, a into b plus c equal to a into b plus a into c. The fourth one is existence of additive identity. There is an element in f which we denoted by 0. For all a in f, a plus 0 equal to 0 plus a equal to a. The fifth property is existence of multiplicative identity. There exists an element in f denoted by 1 such that a into 1 equal to 1 into a equal to a. Here 1 not equal to 0. Similarly, existence of additive inverse. For all a in f, we can find an element minus a such that a plus minus a equal to 0, which is equal to minus a plus a. The next property is existence of multiplicative inverse. For all a in f, we can find an element 1 by a or a inverse such that a into a inverse equal to a inverse into a equal to 1. The next topic is order relation in R. The first relation is law of trichotomy. If a comma b belongs to R, then exactly one of the following inequality is hold. Suppose a is less than b or a is greater than b or a equal to b. The next relation is law of transitivity. If a comma b and c belongs to R, then we have a is less than b and b is less than c implies a is less than c. The next relation is law of compatibility with respect to addition. If a comma b and c belongs to R, then we have a is less than b implies a plus c is less than b plus c. Similarly, for addition, the compatibility of addition, we have to follow the law of compatibility with respect to multiplications. If a comma b and c belongs to R, then we have a is less than b and c is greater than 0 implies a into c less than b into c. And a is less than b and c is greater than 0 implies b into c is less than a into c. Next, I am going to take the concept of upper bound and lower bound. First, see the definition of upper bound. Suppose that So capital S is a non-empty subset of R. R is the real number. If there exists an element U such that X less than or equal to U, for every X in capital S, then U is called an upper bound of S. In this case, we say that capital S is bounded above. See one example. Consider S is the subset of the real number R. In this case, S is the closed interval 0, 1. Here the number line minus infinity to plus infinity, S is the subset which is in the figure 0, 1. Okay. So in this example, 1 is an upper bound of S, because every element in S, capital S, are less than or equal to 1. That is, for every S, small s less than or equal to 1. For all small s belongs to capital S. In this case, we say that capital S is bounded above. In general, a non-empty subset of R is bounded above if it has an upper bound. Another example is, suppose T is the subset of R, capital T is the subset of R. In this case, suppose T is the closed interval 3, 7. In this case, upper bound of T equal to 7, 8, 9, 10, etc. Here, the element 7 which is belongs to T, but the number 8, 9, 10, etc. does not belong to T. Okay. So, the next example is, suppose P is the subset of S. In this case, P equal to P is the subset of R. In this case, P equal to -1, 0, 1,